Okay, this is our third week. In the first week, we made a brief introduction to artificial intelligence, and last week, as you remember, we started with linear regression. This week, we will be working on multiple regression, robust regression, and performance evaluation. This week is going to be somehow continuation of the previous week, so I hope you reviewed the material of the last week. Even if you didn't, we will spend the first 10 minutes of the course to review the last week's material. So, the outline of this week is we will start with a summary of the previous week, and then we will see robust regression. Then we will spend some time on performance evaluation. Then we will talk about multiple regression. Then we will work on regularized regression. We will see polynomial regression, and then if we have time, we will work on variance bias trade-off. So it looks quite crowded. It actually is. That's not going to be an easy week. Last week was not an easy as well, but I hope it's going to get better and easier as the time passes. So we will not have so much mathematics this week, but I hope you remember some of the mathematics that we have seen the last week. Okay, so what we did last week is we first had a workshop on data analysis with Iris dataset. We have seen how we can read CSV files where we usually store our data, and then we have seen how we can display the content of a data frame. As you remember, we worked with Anaconda, we used Python, we used some libraries like Pandas, NumPy, Seaborn, and then we have seen how we can visualize data and plot some graph types. Then we started an introduction to the linear regression, and then we worked on this graph. And then we said we have some points, we have some observations, and we have some measurements. And our aim is to find a mathematical model that can model all of these points. In this case, our points are income versus happiness. So as people say, as your income increases, your happiness increases. So this plot basically shows that as your income increases, your happiness increases. And the way to find a mathematical model, a simple mathematical model, we create a line that passes through most of these points. And then once we find this line, we can estimate any of the income versus happiness, right? This was the problem we worked on last week. So we just wanted to create a line that passes through most of these points. A simpler example. So we had some observations, we have some predictions or measurements. So the observations are the x-axis, the measurements or the predictions are the y-axis. Once we plot these points in the Cartesian coordinate system, we see a shape something like a line, right? So the aim of the linear regression was to find the best line that passes as close as possible to all of the points. So this was the problem we wanted to solve. And once we have our x and y coordinates or observations and measurements, we had some equations where we find the best line that passes through most of these points. And in order to derive this, you remember the equation of the line y is equal to a times x plus b. We spent some time to derive how we can get a and b, okay? And we have seen that we had to minimize an error function, a mean square error function, and then we said we have two equations and two unknowns, and our aim was to predict a and b. One was the slope, if you remember, the other one is the intercept. Once we predict a and b, we were basically there. We had a line, okay? So we spent some time to derive these equations, and we have seen that we have two main equations. One equation is for a, and the other equation is for b. Then we have seen another way of deriving this. This is called least square derivation, and this is called linear regression with overdetermined matrices. That's basically more or less the same. What we are trying to achieve is we are trying to find A and B. So we are trying to create a line equation, right? And the equation we are trying to create is y is equal to a times x plus b. And we have n observations, which means we have n x's and n y's. We put them on a column-wise matrix, the measurements, and we put all the observations and other metrics. And this is what we would like to solve, A and B, okay? And we call this matrix here, or this vector here, W, and we call this matrix here, which contains our observations, X, and the matrix that contains our measurements, Y. And in order to find W, we want to solve W because it contains our coefficients. The A and B are called coefficients. These are our unknowns. Remember the equation y is equal to a times x plus b, right? So we would like to find A and B. And the way to find W is using this equation, which is basically called pseudo-inverse or the false inverse. Please remember this formula. You don't need to remember the derivation of this formula. We will use this formula for this lecture, for today's lecture as well. So just remember three things. We have these equations. If you would like to find A and B from your observations, this is easier to program. This way of derivation is easier to program, but this way of least square solution is more useful because it can be generalized easier. Because today we will see we don't need to have one x. We can have multiple x's with our observations. So let's say we are doing an experiment and we measure not one thing, but let's say we measure three things. Then we will have more than one axis here, right? And if you would like to solve these equations with more than one x, that's more complicated, but it's easier to solve by using the pseudo-inverse. So we will be using this equation from now on for this lecture. And we had an example on Jupyter Notebook. We loaded the Boston House zinc price prediction. We used one of these columns. So this is the price of the house. And these are some attributes like the room number, the tax. We tried some of these values and tried to make a prediction on the house price. But please remember, we just use one of each column for the operation. We didn't use all of these columns, okay, for the previous week. This week, with multiple regression, we will see how we can use all of these columns together. And we will see whether it's beneficial or we don't need to use all of these columns in order to make a prediction. So that problem is called multiple regression, when you would like to use all of these columns or more than one attribute. And now we have seen how we can find the correlation between all these attributes, and then we have seen how we can make a prediction. We used another library called scikit-learn, and we used the linear model, linear regression for our previous course, and then we have seen how we can create a model. This is the model creation phase. We have seen how we can fit or we can feed or we can train this model with our x and y, the measurements and predict observations. And then we have seen how we can use this model to make a prediction. Okay, so this is the quiz from the previous week. That was quite easy actually. Anaconda, as we have seen, that's a popular Python distribution platform. The notebook we used for the previous workshop was Jupyter. We will be using the Jupyter notebook a lot. Up until we will deal with deep learning, we will be using Jupyter notebook. You can still use the Jupyter notebook with deep learning, but we will switch to Google Colab for that part of the lecture. Which command we use to read CSV files with pandas? That's read CSV. That's CSV files, read CSV. Which pandas command we use to display the first 5 rows of data? That's head. If you want to display the last rows of the data, that's tail. And these are quite useless. There is nothing like it, or there is something called exec. Which of the following is a graph type? We have seen like 20 graph types in the previous lecture. Histogram is a graph type, violin plot is a graph type, box plot is a graph type. If you don't remember these plot types, please go and check the previous lecture slides. And the correct answer is all. What's the equation of a line? You should know this. This is important. You definitely know this. If you didn't answer this question correctly, please watch the previous lecture again and review your linear algebra classes. Pandas is a data analysis library. That's a pretty easy question. Linear regression can handle noisy data very well. That's false. We had seen this in the previous lecture, and we will start by seeing this in this lecture, this week's lecture. Which can find the inverse of an overdetermined matrix, that's pseudo inverse. The minimum of a function is located where its first derivative is equal to 0. That you should know from your high school or calculus studies. So that was basically pretty much from the last week. Okay, so we will start with robust regression. So what I mean with robust regression, let's use this applet for a second. So this is a pretty handy applet. Let's add a point here. Now we have one point. I added another point. Okay. Once I click this here, that's showing me my least square line. So this is the linear regression we studied last week with just 2 points. Let me add one more point. So remember, what was the aim of linear regression? We would like to find this line that's passing through most of the points. Okay, I have 3 lines right now, and my line is pretty okay. Let me add one more point. My line is quite okay still. The more points I have, I feel like my line is quite okay, right? But what if I add another point here? My line is pretty off. I mean, this is an outlier. This is not supposed to be here. But since all points contribute with the same amounts, this line is destroying the whole linear regression equation. Let me add another point here. So that's even worse. Even if I add some points, my line is still not good. Okay, so this is basically the curse of linear regression. All points are trying to contribute in the same way, and their distance is determining their importance. This is a distant point. This is not actually important, but this is an outlier. But it's destroying the whole stuff. So this week we will see how we can overcome this. How we can overcome these outliers. If we have a noisy data, this is called a noisy data. I mean, if you had this is an okay data because most of your points are along the same line, right? But these guys are called outliers, and if you have points like this type of data is called noisy data. Now we will see how we can deal with this type of noisy data in this week's lecture. So you can use this applet and you can give it a try. I mean, just to understand the linear regression in a better way. That would be pretty beneficial. Okay, so our robust regression method is called RANSAC. That's Random Sample Consensus. Okay, as the name suggests, there is some random stuff going on. And why it is called consensus? Because that's going to be a consensus among all the points. That's a pretty simple method actually. That's a very simple but very effective method. You see this data, this is really noisy data. I mean, you need to find a line that's passing through most of these dots. These are all noise. If you apply linear regression, you will come up with something like this. So this is definitely something we don't want. But with Ranzek, we will find a very nice line. So we will be starting with a data set, and we will iteratively find a model that's fitting all these points in a good way. So this is the least square fit of the same data. You see, this is not good. This is very bad. I mean, the good line is supposed to be something like this. This is a very bad line. So how we do the Ranzek? That's a pretty simple algorithm, basically. You will not be implementing Ranzek. You will be using Ranzek from scikit-learn or from another library, but you should understand how it works, because this is a general model. This is not just to fit a line on data. You can use this to fit a cube or a circle. You can use it for anything. So you should understand how we do the process. We start with randomly selecting minimal subset of points. So what does minimal subset of points? That really depends on the model you would like to use. So for this set, we would like to create a line. And remember the equation of a line, y is equal to a times x plus b, right? We have a and b, and we have x and y, which means we have actually, we need 2 points to fit a line. If you remember from your previous studies, you just need 2 points to fit a line, right? So this is the minimal subset of points, 2 points for fitting a line. So we randomly selected these points, okay? Now I have 2 points to fit a line. Then hypothesize a model. So my hypothesis is supposed to be a line, because I'm trying to fit a line, and I created a line by just using this first and second point. This is the line passing through these points, okay? That should be pretty clear up until now. So this is the line that I could create from my 2 randomly selected points. Then I need to compute an error function. And my error function is basically the sum of errors for all the rest of the points, right? For this point, for example, the error is the distance between this point and this line. And for this point, the error is basically the distance between this point and this line. And once I calculate the distance of all these points to this line, then I get a total error for my prediction. Okay? And then I select a boundary. I select an error boundary for my line. And this green dots represents the error boundary of my predicted line. And I calculate how many points I have inside my boundary. So I have like 1, 2, 3, 4, 5. I have 9 points inside the boundary for this predicted line. So this was my initial randomly selected line. Then I repeat this process until I find something meaningful, or until I am confident that my line is okay. So this is another hypothesis, for example. I randomly selected these 2 points, and in the boundary I have 4, 6, 7 points. That's not bad, but that's worse than my previous prediction. So this is another prediction. I randomly selected these 2 points, this one and this one, and I have more points inside my boundary. So this boundary is same for all my predictions. The distance between this boundary to my prediction line and this boundary to my prediction line is always same. But the number of points that are inside this boundary, this increased. So this prediction is a better prediction than my previous 2 predictions. And this is another prediction, and this is the best prediction I could get. Okay, I randomly selected these 2 points. I could have selected this point and this point, or this point and this point. The thing is, my chances of selecting the correct point is higher. Therefore, I'm choosing randomly, because most of these points that are supposed to be on the same line actually inside a boundary. So even if I choose points randomly, it's quite possible that I will be coming up with the correct points that will be representing my best line. So that's basically how Ransack works. That's pretty easy, that's pretty powerful, and you can fit almost any model with these methods. So this is, for example, a circle, you see, and then I could use the same technique. I need 2 points to fit a line. I need 3 points to fit a circle. I randomly select 3 points, and then I predict the error between all the points on my predicted circle, and then I repeat the process until I come up with something meaningful. So these are some basic examples from image processing. For example, if you want to find the boundaries, if you want to fit a line on an image, Ransack is a pretty robust and pretty much used technique. So this is a number plate. You see, this is not a straight, perfect line. There is so much noise, and if you try to use linear regression, that could work here, right? That's okay. It might work here. That's fine as well. That is quite likely to work here, but it's not gonna work here. This is too noisy. And if you use Ransack, that's fitting almost perfectly. See, and for example, here we have some buildings, and we would like to find the facades of the buildings and the lines on those facades. You can use Ransack to do that. And as I said, you don't need to find lines. You can just use Ransack for anything. You just need a mathematical model. And then you need to know how many points you need to hypothesize that model. For example, you can fit circles and you just use Ransack. And you see, with such a noisy data, you can fit circles. Okay, so before we go into the performance evaluation part, I would like to go through the first Jupyter Notebook stuff. Okay, so we will have 2 examples on Ransack. The first example is going to be a simple example. You can find the link here if you would like to repeat or you would like to read the article. Do you remember from our previous lectures, from our Anaconda Navigator, we just selected our virtual machine learning, and then we just press this launch for the Jupyter Notebook. Now we have our Jupyter Notebook. We can just press Shift Enter in order to execute all the cells. So I just pressed Shift Enter, that executed. It imported pandas as PD, and it read Ransack data.csv. I sent this data set to you, and I think you can download it from this link as well. So let's check what we have. That's a simple data set. We have hours and score. That's some basic data set. So let's plot it. The thing is, this part of the data looks like a line, right? But this is basically noise, and we know from our experience that linear regression is not going to work here because we have noise here. So we create our input and output array here, and then let's first check how linear regression will behave with this kind of data. So remember from our previous lecture, we created a linear regressor here. We created the model, and then we used the function fit in order to fit a line here. That's a line because that's a linear regression. If this was another model, then the fit was going to hypothesize that model. That's X, that's Y. I just named this as input and output, but it could be just X and Y. And the way we take this is, remember from our previous lecture, this is a data frame, and this command is just taking the first column of the data frame, and this command is taking the last column of the data frame. Okay, so we created a linear regression model. We fit a model into our data. Now let us see how does it behave. As expected, since we have so many noise here, so much noise here, the linear regression model couldn't find a good prediction, right? There is so much error here. So what we have seen is we assume that Ransack is gonna behave in a better way. So we will be using again scikit-learn linear model Ransack regressor. This is still a linear model, okay? And please remember what we did for linear regressor. Instead of Ransack regressor, what we wrote was here is linear regression, right? Regressor is linear regression, and then we use the fit function. It's exactly the same thing. We just import the mathematical model we would like to use. In this case, that's a Ransack regressor. And here I created my model, like I did here. Linear regression. Regressor is equal to linear regression. This could be regressor is equal to Ransack regressor, right? And what I had done was using the fit function, which was going to use linear regression in order to fit. And here I just use Ransack with the same command. Okay, that's the good thing with the scikit-learn. You have the same process for almost everything. You create a model, you create an empty model, and then you fit or train this model by using the fit function. And then basically you can use the predict method in order to make prediction with your mathematical model. Okay, let me so that basically created my Ransack regressor and then fit my model. Now let us plot this. See, this is way much better than the previous one. And if you would like to see both predictions on top of each other, this is just basically doing that. As you see, the green line is the Ransack and the blue line is the linear regression. Linear regression is pretty off, but Ransack is executed in a very nice way. So basically, if you have noisy data, you should use Ransack for less error. And if you have noisy data, don't use linear regression. That's not gonna work in a good way. We will see some regularization methods that might be actually dealing with noise, but using a method like Ransack is easier and that's much more robust. Okay, now let's make another example with our previous Boston housing price prediction dataset. Okay, let's remember we were importing some NumPy. That's our numeric library pandas for reading and displaying content of data. We will be using scikit-learn again, and you don't actually need to import the system, but you can just do that. And then we will be importing these guys in order to plot matplotlib and seaborn just for displaying our data. Okay, so let's read the content of our housing data. You remember from the previous lectures we had 14 columns. 13 of these columns were attributes, and the last column is the median value of the house, the median sale value of the house. Okay, so that's the price. This is the thing we are trying to predict, and these are our observations, like the crime rates, number of rooms, the text, and most of other stuff. These are the attributes we will be using, and we will be using the same dataset for the rest of our lecture this week. So it's a good idea to understand what these columns are. And we will be using all these columns or some of these columns in order to predict the median value, median price of the house. So this is basically the same commands we used for the last week. Since we don't have the column names inside our data, we specifically load the column names into this variable called code name, and then we assign this code name to the data frame columns. Okay, so now our data is ready. Okay, so let's check what we have with data frame.head. We can see the first 5 rows of the data. That's basically the 13 columns attributes and 1 column measurement. So this is basically some text I added. If you follow this Jupyter notebook, you can read it yourself. It's basically summarizing the steps of Ranzek that we had seen. That's pretty simple. You select 2 random points. In our case, we select 2 points randomly. We fit a line. We measure how many points are inside the boundary that the line spans, and then we create another line with 2 other observations, and we repeat that process until we find the best line possible. So as I said, before multiple regression, we will be using just 1 column of this data. So we have 13 attributes. We will be, for example, using the room number, RM, for our example. So X basically is the room number, Y is basically the house price. So we assign X and Y with this command. And then we import Ranzek regressor. And here we create the Ranzek regressor. Then we fit with our model, right? Okay, so this inlier mask is basically getting the points that are inside the error boundary that we created with the Ranzek, and the outliers are basically the ones that are not inliers. These 2 commands are performing that. So the content of inlier mask is actually either true or false. And if you look at the shape of, for example, inlier mask.shape, let's say, we had 506 rows, and for each row we have either true or false. So for the for example, first row, that point is basically an inlier. For example, the 23, row 23 seems to be an inlier as well. Okay, so let's do some predictions, and let me just draw what we have, then you will understand in a better way. So this is basically the data, right? This is room number, this is house price, and then this is the line we predicted. The blue ones are the inliers that we were discussing. So these inliers are the points that are inside the error boundary. So the error boundary for this line is this one, right? And these red dots are the outliers. So what was this guy basically? So we created some points between 3 and 10. Okay, and then we made a prediction for all these guys. So this is the prediction for 3. If you have 3 rooms, that's supposed to be the prediction. Let's see. If we have 3 rooms, we should have a price around minus $11,000. This is not possible anyway, but so That's the problem with regression. I mean, you can't have a minus price, right, for a house. This is pretty stupid. But since we don't have any other values here we can use, we are making a prediction and we assume that this linear model should predict everything correctly. So we see our prediction is quite okay. But let's see, for example, if we had 5 rooms, we were supposed to have a value around 10,000. Okay, so this is supposed to be the 1, 2, 3. So that's 1, 2, 3. This is around 10, right? So our prediction is working in a good way. So let's check. If we have 6 rooms, we are expecting something around 20,000 because most of these guys are around 20,000. And if you look at our prediction, this is around 20,000. So I would say our model is working in a good way. Okay.
Hocam merhabalar. Tam inliner'ları neye göre seçmiştik acaba? 0'la 32 arasındaydı ama.
Şimdi inlier dediğimiz şey şu. Bir tane şey predict ediyoruz ya. Line predict ediyoruz ya. Bunun belirli bir uzaklığı içerisinde kalan noktalar inlier. Bu uzaklık değişken olarak verilebiliyor. İlk şeyi yaparken zaten hangi line'ın en iyi line olduğunu hesaplamak için bir boundary yaratıyoruz ya şurada. Predict ettiğimiz line'a paralel 2 tane boundary yaratıyoruz. O iki line arasında kalan noktaları sayıyoruz. Şeyin yaptığı da o aslında. Yani inlier dediğimiz o iki line'ın arasında kalan noktalar.
Yani kendimiz seçiyoruz gene o uzaklıklarını.
Uzaklığı kendimiz seçiyoruz. Evet. Default bazı şeyler kullanıyor tabii ki ama uzaklığı kendimiz değiştirebiliyoruz. Dokümantasyonuna bakarsanız scikit-learn'de onu nasıl değiştirildiğini de görebilirsiniz. So the question was actually how what are these inliers? If you remember from the theoretical part of the course, we predict a line by using 2 points, and then we count the number of points that are inside a boundary, error boundary. And inliers are the points that are inside this error boundary. So that was the question. And we can basically print the coefficients of our Ranzek line. You can just give it a try. You can use this as a and b, and by using the y is equal to a times x plus b, you can use these numbers to see if you can get the numbers correctly. So let's do these examples quickly as well. We used room number. Let's use Elstat, which was, I don't remember what was Elstat is. Elstat is the lower status population. So okay, we use the same technique. We just changed our x. The aim was to predict y. That's basically the distribution of our data. This is an okay fit, I would say. Since this is a linear regression, or since this is a linear fit, you wouldn't expect something better. So the better way to predict a value here is to fit a curve, something like this, right? And in polynomial regression, we will see how we can fit a curve into this type of data. But for now, since we are dealing with lines, this is as good as you can get. And this is our Ranzek line. Again, these are the inliers. These are the points inside our error boundary. And these are the points outside our boundary. If we were using linear regression, trust me, you would be getting something like this. That would be so much off. Okay, so let's start the performance evaluation, and then we will take a break after the performance evaluation part. So what is performance evaluation anyway? Why do we need something like this? So up until now, we had seen two ways of creating mathematical models: one linear regression and one Granzek. So what we did is we created some mathematical models. But once you create a model, or once you hypothesize on something, you need to find a way to evaluate your performance, because you need to see whether your model is working in a good way, or you need to see whether your model is totally wrong or not. For example, remember the last plot we worked on? That was a curve, but we were trying to fit a line. So the model was wrong, but we could get as good as possible with the linear model. Therefore, we need to somehow evaluate our model so that we can basically see whether we are using a good model, and if we are using a good model, good mathematical model, whether we are using good parameters. These are two different things. Whether we use the right model, for example, if you try to fit a line to a curve, however you perform, which parameters you use, that's not going to be a good fit. So you need to select the right model, and then you need to select the right parameters for that model. So in order to do that, to evaluate how good our model performance is, what we usually do is we split the data set into train and test set. Okay, and then we just use this train set. Remember our fit function. We create our model, and then we use a function called fit to train our model, right? So we usually just use this training set. We don't use this test set for the learning process, because we don't want our model to memorize or learn everything inside our observations. We will see why we don't want that. But just for now, please remember, we need to split the data set into two, train set and test set, and we should basically use just the training set to fit a model or train our model. So how we basically do that with scikit-learn? Let me show you that, and we will take a short break. So in scikit-learn, there is a part called model selection, and from model selection we import train test split. This is basically splitting your data into train and test automatically. Okay, let me evaluate that. Okay, so we have our data frame. We need x and y variables. We were using the room number as the x value, and the house price as the y value. Let's evaluate these guys as well. So this is basically the command from scikit-learn train test split that will create our training and test set. Okay. So let's see the arguments. The first argument is x. The second is y. We will be splitting x and y into x train, x test, y train, y test. So we have now 4 variables. And the test size determines how much content you want inside the training, or how much content you want in the test set. So 0.2 means I would like to have 20% of my data inside test data set, and I would like to have 80% of my data set inside the training. And this random state 0 means I don't want anything random. So just if you repeat this same command like 20 times, you will always get the same guys in the training and test set. If this is not set randomly, if this is not set to 0, then you will have some random state, which means every time you split your data into training and test, you will have a different training and test. So for repeatability, I would suggest you use random state usually as 0, because when you train something, it's a good idea to use the same training and test set when you repeat the process. Okay. So let me give you an example. Let's say I have 100 points, 100 samples, 100 X and 100 Y's. Okay. And I would like to have 80% of these points to be used in training, and I would like to have 20% of these points to be used for testing. So you will be understanding in a better way once we go through the examples. But just understand, if we mix the train and test set, if we use all points for training, then it's highly likely that our model memorizes the data. So that reduces the generalization. We will be working on what this generalization means and why it is important. But for now, just remember, when you create a mathematical model, you would like it to be as general as possible. If your model is too restricted, that means if the model sees a data it didn't see before, its behavior would not be robust. That means you should create a model that's generalizable. And for this generalization, you just use some part of your data for training and then some part of your data for testing. And there is never and ever an overlap between training and test. I hope this makes sense a little bit. So let's do the same thing. We create a linear regression model here. Okay. LR is equal to linear regression. So beforehand we were using X and Y, right, for training. This time I didn't use X and Y. I'm just using X train and Y train, right? I'm just using 80% of my data for prediction. And now I will create a Y train prediction and Y test prediction. Remember, I have 80% here. While I'm doing this prediction, I'm feeding all the data I used for learning. And let me do this, and let me do this as well. This is basically prediction on the data I didn't use for training. So this is my test data. So what I would expect and what we will be seeing in the next lecture is the error I did here is supposed to be small, because this is basically the X values I used for training. So I use this for creating my model. And since I'm minimizing the error, I should have a log error here. But I have never seen this set when I was doing my model creation, right? That means my error is supposed to be high for this one. In the next lecture, we will see how we can evaluate these errors. We will see 3 methods, and then we will see why we use training and test sets, and we will see how much error we make with the training, how much error we make test. Okay, so what we have seen is we should separate our data into test and training set, and we just need to use the training sets for training our data or for fitting a model, and we should use the test set in order to evaluate the performance of our model. So how do we actually evaluate the performance of our model? We will be seeing 3 types of performance evaluation measures for regression. The first one is residual analysis. Residual means what is left, actually, in English. So that's basically evaluating the distribution of error for the training data and the test data. then we compare the distribution of our predicted values versus the error for both train and test set. If the distribution of test data is randomly distributed over the horizontal axis, then it's good. I mean, if you are close to this axis, if you are here, you have no error, right? So for this point, for example, the error is almost zero. And if you are here, then you have pretty much the worst error you would have for this model. And once you look at this plot for both test and training data, what you see is their distribution is more or less same, and their distribution is close to this line. So if you had a distribution for training set, that's something like this, but if you had a distribution for test data somewhere here, that means your model is actually off. That's basically how you use the residual analysis. You usually use it for visual evaluation of your model. And you just evaluate this type of graph. And if you see a fairly similar distribution between your test set and training set, that means your model is performing well. That means your model is actually general and it can perform well enough to model your test set. Remember from our previous lecture, while we are doing training, we just use the training data, which means this distribution here for the blue dots, these are the errors I make for all the points that I used for model creation or learning, right? And for all these orange dots, these are for points I have never seen while learning. So these are new to the model, but my model is good enough to make predictions pretty similar to the predictions I made for the training data. So just to summarize, we use residual analysis to check the distribution of my error for both training and test data, and I make a visual inspection whether the distribution of my training error and testing error is similar and whether this error is close to this horizontal axis. If it is randomly distributed around this axis, and if these two distributions are similar, that means your model is doing well and your model is making a well generalization. Our second performance evaluation model is mean squared error. This is something we have seen last week actually for the derivation of this square error. Remember, we had to minimize something, we had to minimize an error function, and the error function was basically the mean squared error. The average value of sums of squared error cost function, that's useful for comparing different regression models, and we use it for tuning parameters via grid search and cross validation. And in scikit-learn, we use mean squared error in order to calculate the mean squared error for our regression model. We will make some examples for that, so don't worry for the coding part. And the third model that we use for evaluation is coefficient of determination, but that's usually called as R-square error. That's basically this equation, that's 1 minus SS residual divided into SS total. This SS res is calculated by the sum of our observation minus prediction square, and this part of the equation is usually calculated as the total sum of squares, but this is the mean prediction. That's called the mean prediction or mean observation. And just remember this: the closer R square metric is to 1, the better your model is. Let's see why. So if you look at this part of the equation, if this part is 0, then r square is 1, right? And how can you make this part of the equation 0? This part is supposed to be 0, right? If you look at this, that means every prediction you make, these are the predictions you make, is supposed to be perfectly aligned with your observation, which means your prediction is supposed to be exactly the same as your observation. So ideally, you have a value 1 for a perfect model, but you will never have a perfect model. Trust me, that's never ever gonna happen. And the closer you are to 1, the better your model is. And if you are below 0.5, that means something fishy is going on, and you should check your model or your parameters. There's something totally wrong. Okay, so before we dive into multiple regression, we will go through some coding. So remember this part from our previous lecture. We split our test data and training data. This part is important. We made a prediction here with our linear regression model, but we created our model and we made the learning with just our training set, right? We just used the X train and Y train. We didn't touch to X test or Y test. So for evaluating the performance of our model, we will calculate two predictions. The first prediction is for our train set, and this is the part we expect somehow less error, and this is the part we expect more error, because we are making predictions based on our test set. This is the set we have never seen, right? So the error is supposed to be bigger than this. That's quite usual and quite normal. Okay, so let's check the residual analysis and try to understand whether our model is doing okay. So remember from our theoretical part of the course, the blue dots are coming from our training data and the orange dots are coming from our test data. So the distribution for our training data set and test data set is quite okay. They are pretty much similar, right? So this is okay. And if we take a look at the centroid of our graph, most of the data is accumulated below this line, which means they're pretty close to 0. So they're randomly distributed along this black line, which is 0. And the distribution of the training data is close to the distribution of the test data in terms of residuals or in terms of error, which means my model is doing fine because the error is kind of okay. It's not doing so much error even for the training data or the test data, and it's general enough so that my testing predictions are quite close to my training predictions. This is the first method we use for evaluating the performance of our model. We can use this residual analysis for most of the models. That's an evaluation method for regression, and that's being used for visual inspection. And you just determine whether your model is good and whether your model is general enough. Okay, so coming back to the second model, which was the mean squared error, that's basically the equation. We still use the scikit-learn, and then we basically use this command, mean squared error. We will first find the mean squared error for our training predictions, and then we will use the same function for our test. So let's look at the parameters of the function. That's y train, which means these are my measurements, right? These are the correct values. These are the values I am trying to find. And these are the predictions that I made with my mathematical model. So ideally, if my model is perfect, I should have the same numbers for my y train and y train predict, because my model is working perfectly. So whatever x value I give, I get the perfect y value. But that's never gonna happen, right? So let me calculate the mean squared error for the training set. And this command is going to find the mean squared error for the test set. So I would expect a greater value, because here I calculated basically the mean square error for the training. So I used these x and y values for learning. I used these guys to create my mathematical model. So the mean square error is supposed to be smaller. And let's see. You see, the mean square error is bigger for my test, but it's not significantly bigger. Right? This is a pretty good model, actually, because the mean squared error is pretty close for our test set and training set. And if you look at the residual analysis, what we have seen is correct, because the error distribution of my training and test data is quite similar. So with our two models, we observed that our model is good, our model is general enough. Okay, so we have another model, the coefficient of determination, or R2, R square, or R2 error. So let us do the same thing. We import it from the metrics library of scikit-learn, import R2 square. And again, we calculate both for train and test. So remember, if we are closer to 1, our model is better, and the more we get distant to 1, our model gets worse. Okay, so this is not a good score for R2 square, and this is even for the training, actually. And let's see what we will have for the test. That's even worse, but it's not significantly worse, but it's still worse. So remember, if we are close to 1, our model is good, and if we are not close to 1, that means actually our model is not doing well. And we are smaller than 0.5, so there's something fishy going on with our model. So what we have seen actually, we use 3 error evaluation methods. We inspect our model visually, we created some mean squared error, and we use R square method, coefficient of determination, to evaluate our model. For the first two evaluation methods, we said, okay, my model seems to be doing fine, because my distribution for the training data and the test data is quite similar, right? And we calculated mean square error for both training data and test data. They were pretty close, which was a good indication. But then I calculated the R square error, but it's not close to 1, which means my model is actually not that good. My model is not doing good predictions, but my model is doing stable predictions. That's why I have close mean square errors for training and test data. So this is a big number for mean square error. That means this is a bad model, actually. But this is a stable model. It is predicting bad, but it's stable the way it predicts. And this is going to be the case we will be dealing with bias variance dilemma. Your model can make predictions close to each other. That doesn't mean your model is good. Therefore, you should check most of these evaluation methods in order to see whether the model you create is good enough or not. So that was basically the model evaluation part. As the summary, just try to use all three methods. Use residual analysis for visual inspection. You should definitely calculate the mean square error to see how much error your model is doing and whether your model's prediction capability is generalizing the model. I mean, if you have close mean square errors for training and test, that means your model is general enough. But as the last method for evaluation, just use R-square method as well to see whether your model is close to 1 or not. If your model is not close to 1, and if it is actually smaller than 0.5, then you should expect something wrong with your model. So that was basically the part about performance evaluation for our models. Now we will be starting another topic called multiple regression. But before doing that, let's see what does a perfect model looks like. So here we create some random numbers. That's basically the equation of a line and randomly scattered points. This is a perfect model line. This is so good to have in real life. You will never ever have something like this. But this is close to ideal. And if you have something ideal, let's see what happens. We have the same procedure. We will be using the 30% of the data for testing and 70% of the data for training. Again, we will not have anything random. And we will be using linear regression, and then we will be doing a prediction for our training and test set, as we did in the previous example. Okay, so let's see how does the residual analysis looks like. So perfect. So all the points are distributed randomly around 0. That was the first condition we were checking with the residual analysis, right? And the distribution of the error for the training data, which is this axis, is almost exactly the same as the distribution of the error for the test data, the orange guys. So with the residual analysis, I can just say this model is perfect because these dots are perfect. So concerning the mean square error, if you remember the mean square error for our previous example, it was something like 40. That's like 1. And this was mean square error for the training. We should expect something slightly higher because the data is quite perfect, so it might be even better than the training. This is pretty unusual since the data distribution is so perfect. Our mean square error for the test is smaller than the mean square error for the training. This is like impossible. And if we check the R-square, that's very close to 1. Remember, the better we get close to 1, and this is almost 1. That means that's almost a perfect model for the training. This should be slightly smaller than the other value. It's even better. It's even closer. So when you have ideal data, which you will never ever have, then you see what happens. You get very close to 1 with the R-square metric. You get very small mean square errors. Remember with our previous example, the mean square error was like 40. It's very close to 1 here. That's very close to 1 here for both test and training set. For residual analysis, we had two conditions. The one being distributed randomly horizontally along this line. And the second thing we were supposed to check with the residual analysis is the distribution of training data residuals and test data residuals, whether they have the similar distribution or the same distribution. As you see, if you have perfect data, then they are perfectly aligned with each other. As I said, that was to show you what happens if you have perfect data. You won't have perfect data anywhere in your machine learning life. But if you have perfect data, then you have a residual, something like this. You have very small mean square error and you have very high R square coefficient of determination, which is very close to 1. Okay, so that was basically it for the performance evaluation. Now we will be starting with the multiple regression part of our course. So, what is actually multiple regression? In the last week's lecture, we have seen the simple linear equation y is equal to a times x plus b, or you can represent the same thing as you take the b and you call it as beta 0, you call a as beta 1, and this is exactly the same equation we used for the last week's lecture, right? This is the equation of the line. But what happens if you have more than one x, which means if you have more than one observation? So we had checked, we had an observation about the income versus happiness, right? This is one observation, one measurement, one observation, one measurement. Up until now, we had just one observation. We had 13 observations for the Boston housing price data set, but we only used one column for each of our experiments, right? We never used more than one column. But it's possible to actually use more than one attribute when we do regression, and that's called multiple regression. And mathematically speaking, this is the line equation from the last week. And if we have more than one x, then we will have more than two coefficients. The first coefficient was this guy, which was b in the last week's lecture, and this was a. Now I would like to call these guys as beta, because I will have more than one beta, more than two betas in this equation, and we can have as many attributes as possible. Then this equation can be written as y is equal to beta 0 plus beta 1 x1, beta 2 x2, and blah blah. So we have more than one independent variable. That's why it's called multiple regression. Remember our Boston housing price example? We had 13 columns, which means we actually had 13 observations, and from these 13 observations, we made a measurement on something. And in that case, it was actually the house price. So I measured 13 things, and then I came up with a measurement. That's basically the theory of multiple regression. And the mathematics actually behind this is, remember from our summary of the last week, this is the pseudo-inverse formula. And since this is a matrix, and last week's example, we had this equation. y1 is equal to a times x1 plus b. y2 is equal to a times x2 plus b, and yn is equal to a times xn plus b. But this time, we don't have just x1. We have x11, we have x12, we have x1n. So the equation is quite similar. For y1, we have a1 times x11, we have a1 x12. So that's going like this, okay? And we just use the same, basically the same pseudo-inverse formula in order to derive the multiple regression. So things to understand about multiple regression. If we have too many correlated variables, we will see what that means actually, what correlation means. Then x becomes singular, and if this part of the equation becomes singular, then the result becomes unstable. And when columns of x are highly correlated, this part of the equation becomes nearly singular, which means it's not invertible, and this is the inverse operation, remember. And if this part is singular, then this part becomes unstable. It becomes non-invertible. So high correlation is not good for multiple regression. And this multiple collinearity occurs when independent variables in a regression model are correlated. And this correlation is a problem because independent variables should be independent, as the name suggests. So if you change something, that changes effect should be independent from everything else. And if two variables are correlated, that means if you change one variable, the effect of this change affects the other variable. And if they do not behave independently, that means they are correlated, and that creates something called multicollinearity. And we will actually see how we can detect multiple collinearity and how this affects our predictions. Here, just understand you can use more than one variable for the regression problem, both for linear regression or polynomial regression that we will be seeing at the end of this course. And if we have highly correlated variables, that may make our predictions unstable, that may make our model unstable. And we will see how we can deal with that. You can just throw away these correlated variables, or you can just use them in your model. That doesn't really affect your predictions. But if everything is correlated with each other, then your model will be very unstable. And we will be seeing this on some examples. Let me. So that's multiple regression. So remember, this is the equation from last week. This is the equation of the line. We have one independent variable here. For multiple linear regression, we have more than one independent variable. This x1, x2, these are the independent variables that are more than one, right? Okay, so let's check the code and try to understand what's going on. As usual, we imported our numerical library, pandas, matplotlib, seaborn, scikit-learn, and the system. We will be using the housing data, the Boston house price dataset for this example as well. And since we didn't have the column names for this data, we will be loading the column names by hand. And we use the data frame.head in order to check the content of the data. As you see, this is our y. This column is our y, the median house price. And these 13 columns, the remaining 13 columns, these guys, are our independent variables. Remember from this equation, if we use just one column, as we did in our previous examples, for example, we used RM, right, the rule number, then we apply this equation. It's this equation. That's normal regression, normal linear, simple linear regression. But if we would like to use more than one column, let's say we would like to use room number as well as text, right? We have two independent variables then. We use two attributes. Then your equation is this one, beta 0 plus beta 1 x1 plus beta 2 x2. So then it's called multiple regression, right? If you have one independent variable, it's simple linear regression. If you have more than one independent variable, then you have multiple regression. Okay, so let's load our data into X. So what this is doing is actually it's getting all these columns into X except the last one. We are neglecting the last column because we will be using this as the Y value, right? This is not independent variable. This is the Y. These are the X values. So these 13 columns are the X values. This is the Y value. That's why we are skipping that. And if you check the shape of X, we have 506 rows and 13 columns. These 13 columns. Okay. And if you check the shape of Y, we just have one column, and it's this medium value, medium price value. Okay, so as you see, we are still using the same thing actually. Remember from our previous examples, we were using linear regression. We are still using linear regression, so it's basically the same command for creating the model. So we are basically using the same command. We are using linear regression, right? It's there is no difference, and we use the same command fit. And scikit-learn basically understands because you have 13 independent variables, it's gonna use multiple regression. If we had one independent variable, it was going to use simple linear regression model. So that's the good thing about scikit-learn. You don't need to worry about number of your independent variables. Scikit-learn is taking care of that. It's using basically the same structure, the same model. In the fitting process, it's taking care of the number of your independent variables. Okay, so now let's try our model with the second row of our data. This is basically the second row of our data. We can see the content of our second row. You can check it basically 0, 1, 2, and you can check whether this number is correct. And let's make a prediction. So it's again the same. It's basically the same command we were using in our previous lectures. That's just linear regression.predict. It's exactly the same thing. And now let's make a prediction. And now we know how we can evaluate our models actually. Then let's use R2 score to make an evaluation. Now we used all the data actually for prediction and testing. That's not a good idea if you remember from our previous discussions. But just sake of simplicity, we'll just use all the X values for predictions and then we will calculate an R score, which is kind of okay. But since this is the points we have used for training, this R score is not this measure is not good actually. That's not a very good model. And let's see how we are doing with our mean squared error. It's quite big from my point of view. Now let's repeat the same thing, but now let's split our set as train and test set to see how we are doing. So we again calculate the R2 score. That actually dropped because we use because we are using the test set. I mean, here that's closer to 1, right? Because it was containing every data we used for training. Here we split our test and training set, and we use our training set for learning, and then we just use our test set for prediction. That's lower than this number. That's still above 0.5, so that's kind of okay. And as you see, the mean square error is increasing as well, because here we were using all the data we used for learning, but here we made the learning process with our training data, and we are doing the evaluation with our testing data. Okay, so let's make the residual analysis as well. So if you take a look at the content of our residual analysis, we had two criteria. First one is the distribution of training data residuals. The blue dots are supposed to be similar to the orange dots. It's more or less similar. I would say it's not good, it's not bad. And the second criteria was the dots are supposed to be close to this line, close to 0. They're kind of okay. I would say that that's an okay model for doing the prediction. So remember, from the theoretical part of our course, we said multicollinearity is something bad. We need to detect multicollinearity, and if it is possible, we should take care of that. If we have too many independent variables, and if you don't have all your independent variables collinear with each other, then you can just use them. But if there is multicollinearity in most of your independent variables, then you should start dropping your independent variables. So let's take a look at the example, then you will understand in a better way. So that's basically our data frame. Last week we have seen what this core means. That's basically the correlation matrix. The correlation means how correlated a variable is with another variable. If you see something big in this matrix, that means they are highly correlated. Let's say, for example, text is highly correlated with this is 0.91 rad. So these two variables, these two independent variables, rad and text, are highly correlated, which means they are not really independent. So the change in text is affecting rad, and the change in rad is affecting text, which means they are highly correlated. So how we can actually understand whether two variables are correlated or not? We have two methods actually. We can use visual inspection on our correlation matrix. We will use a heat map in order to do that. So this is how we actually print the correlation matrix. So dataframe.core is creating the correlation matrix, and then you can just print the correlation matrix. Then we need to do some operations to make things simpler. Okay, if we have values that are smaller than 0.6, we can neglect them, right? That means they're not really correlated with each other. So in order to simplify our heat map, we can just use this command in order to make everything that's smaller than 0.6 0. Okay, so for example, this guy was 0.54, right? Here it is 0, because it's smaller than 0.6. So once I evaluate this, I get something like this, right? So it's easier to take a look at a matrix like this. And if we create a heat map, then it's easier to visualize actually our situation. So this is how we visualize this correlation matrix. This is seaborne heat map. You just give the correlation matrix, and then this is just assigning the color space. We should deal with things that are either too bright, like these guys, or too dark. But we don't deal with the diagonal. The diagonal is obviously the same variable is supposed to be 100% correlated with itself, right? So you don't deal with the diagonal. So just skip this and then try to concentrate on the values that are darker than the rest. For example, this one is quite dangerous. That means rad is quite correlated with text. Also, text is quite correlated with indus. So this text, indus, and rad, they seem to be pretty dangerous for multicollinearity. There is, for example, this guy, indus, is highly correlated with nox. This is very high correlation. This is pretty dangerous. The rest is not that important, but this is quite correlated. So this is the visual way of determining which independent variable is highly correlated with the other independent variable. There is another method for detecting multicollinearity. This is called the eigenvalue method. This is a more complex method. If you remember from your previous linear algebra courses, we calculate the eigenvalues and eigenvectors of the correlation matrix. This is the first thing we do. Okay, we calculate the eigenvalues and eigenvectors. If you don't remember these terms, please take a look at your previous linear algebra courses. We will be dealing with eigenvalues and eigenvectors in the principal component analysis lecture soon. But before that, if you want to understand this part, please try to remember the eigenvalues and eigenvectors. But basically, what we are trying to find is actually the smallest eigenvalue. And if we sort of the eigenvalues, we had, remember, 13 independent variables, right? And for every independent variable, the smallest eigenvalue is for the 8th row. And each eigenvalue is correlated with an eigenvector. And if you take a look at the eigenvector, 8th eigenvector, you actually see these numbers. And these guys are actually the highest numbers in the 8th eigenvector. And they correspond to the 9th, 8th, and the second independent variable. And these are the indus, rad, and text. So this is a complicated and mathematical way to find the collinear variables, but you could just do the same with the heat map. I mean, if you take a look at your heat map, you could just see indus, rad, and text. Basically, they're pretty much correlated with each other. So if you want to torture yourself, this is the difficult way of finding collinearity. If you would like to feel more comfortable, you can just use this heat map. That's pretty much up to you. Okay, so let's see what happens actually if we use just correlated variables for our multiple regression. Remember from the theoretical part, if we have too many correlated variables, then we expect our prediction to be unstable. Let's see whether that's correct. So this is our data, and then I will drop all the columns and I will just use indus, rad, and text. Remember, these are the independent variables that are correlated with each other, right? We just drop the rest of the columns from X, and then you see we have just indus, rad, and text in our data frame. So I will make a prediction by just using these 3 independent variables. So if you take a look at the shape of my x, I have 3 columns. If you take a look at the shape of the y, I have just one column, that's the price of the house. These are my independent variables. Again, I will use linear regression. I did my fitting, I created my model, I did my fitting, and then I will be calculating the R2 square, and I will be calculating my mean square error. And I'm not splitting the data into test and training, okay? I'm just using every data I use for learning. And if you take a look at the R square error, this is too low. This is like saying your model is doing not good. Because I just use all the 3 correlated variables. This is as bad as possible for the model. And this is just saying, just fit something that can be as bad as possible. So the R2 score is very bad, mean square error is very bad. And let's see whether what happens if we split this into test and training. I again learn my model from my train set, and then I calculate my R score. See, this is 0.06. This is like the worst model ever. This was supposed to be 1 for the perfect model. This is even smaller than 0.1. So this is really bad. And if you take a look at the mean square error for the test set, this is 76. This is like saying you created a model and that's making predictions like randomly. And if you take a look at the residual analysis, it's difficult to say your model is bad, actually. But if you take a look at these numbers, especially the R2 score, your model is doing really bad. So what happens if we use just other 3 independent variables? So let's say, let me check which variables we dropped. So we have just these 3 variables. These were not highly correlated with each other. So let us just use these guys to see what happens with our model. If you take a look at the shape of our X, it's again, we have 3 independent variables. And once we make a prediction with our test set, as you see, the R score is much better. It was 0.06. For our test set, it's 0.37. And if you take a look at the mean square error, it was 74, 76, and it's 51. It's much better. So the moral of the story, you can use more than one independent variable, and if you use more than one independent variable, it's called multiple regression. In multiple regression, you should be careful with correlated data. If you use only correlated independent variables, then you will end up with a very bad model. But if you use correlated variables plus other variables, then your model should do okay. So just remember these 3-4 things. Okay, you can use more than one independent variable. That's called multiple regression. If you have only correlated independent variable, your model will not do well. So just drop some of that independent variables. If you have correlated variables as well as other variables, you can just use them all. So that's basically it for the multiple regression part. In the next lecture, we will be dealing with regularized regression and polynomial regression. Then we will be seeing something called variance bias dilemma. So we talked a lot about generalization. We said our model is supposed to be general enough so that it can make good predictions. What this means actually? So overfitting happens when a machine learning model has become too attuned to the data on which it was trained, and therefore loses its applicability to any other dataset. So it loses its generalization capacity. So if you take a look at this example, for example, So my model is perfect for this data. I mean, it's passing through every point, almost every point. So this is the perfect model you can have for this data. But its generalization capability is too low. Because if you have a point here, you don't know how this model is gonna behave. Okay, so this is a more general but a simpler model. This is a very simple curve. That's a quadratic curve, but it's modeling in a more general way. So overfitting happens if you use a too complicated model, or if you force your model to learn everything in your training data. So remember, overfitting is bad, underfitting is bad as well. Your model is supposed to be as general as possible. So this is a perfect overfitting example. We have these points, right? So if you take a look at these points, you can just fit a line, and that's kind of an okay-ish model, right? So this line is kind of representing these points. But if you fit a more complicated model, let's say we fit a 5th-degree polynomial or a 6th-degree polynomial, your model is perfectly crossing from all your points, right? This is the perfect model for this data set. But its generalization capability is too low. If you have a point here and you would like to make a prediction around this point, right? This is something like 3.8 or something like this. If you use this very complicated model, this fancy blue model, then if you make a prediction here, it will predict this as 13 or 14, right? But when I take a look at my points, I wouldn't expect a value here. So this simple line, if I were using this simple line, and if I were to make a prediction here, then I would get a point around here, which is more reasonable, right? So the moral of the story, this very simple line is more general than this very fancy, super uber complicated model. And its generalization capability is much higher. So if you use all the points in your training data, and if you force your model to learn everything in your data, that's called overfitting. And this is very bad because you perform perfect on your training data and you perform very bad in your test data. So we will now see regularized regression. This is actually again least square optimization. That's not very different from what we have seen up until now, but the least square methods doesn't differentiate important from less important. As we have seen at the beginning of our course, we created a least square line, we added some noise, then our line was pretty off. So regularization is a way to avoid overfitting by penalizing high-valued regression coefficients. And in simple terms, it reduces parameters and shrinks or simplifies the models. And the model with the lowest overfitting score is usually the best choice for predictive power. So the regularization is basically simplifying your model, or it is selecting the model that has the lowest overfitting potential. So we will see three types of regularization methods: regularized regression. We will see ridge regression, we will see lasso and elastic net. They are more or less same, doing the same thing actually, and we will again use scikit-learn, so don't worry about the mathematics. I know it's quite late right now, I know we are tired. I'm not going to go into the details of the mathematics, but you should understand why we need this regularized method for regression. Assume we would like to fit a line to the dots. Okay, these are kind of okayly distributed lines, and this is a very bad estimation. I mean, if this was the line we fitted this is like the worst line you can fit. And this is a good estimation, right, for these points. So just assume that instead of all this 4, 6, 8 points, I would like to just use 2 points. So these points I randomly selected from this data. And this is this one and this is this one. I would like to fit a line that's representing this data set. But I just would like to use this 2 subset, this subset of this data set. So this is basically the line I would fit. And this was the line I did fit to all the data set. And this is the line I could be able to fit to these 2 points, right? So this is a perfect fit for these 2 dots. But this is not a good estimation for the rest of the samples, right? Okay, this was my sample, all of my samples. I used just 2 dots, and I created a line with least square method without regularization. And this is the line I got. So this is perfect in itself, but it's not general. I mean, it's not representing rest of my data set. Okay. And the main idea of regularized regression is to fit a line with small bias, with small error, so it doesn't overfit the data. So this was overfitting. I used 2 dots, I used least square method, I used everything in my data set. So this is a perfect fit, this is a perfect model for my data set. But since it's a perfect fit for the existing data set, it's not generalizable. If I were to use the regularized regression, this line would have been a much better line that would represent the whole data set. So we will be seeing three different regularized methods for regression. We will be seeing ridge regression, and then we will be seeing lasso, and then we will be seeing elastic net. So ridge regression discourages learning a more complex or flexible model, so as to avoid the risk of overfitting. So basically, all regularized methods try to avoid overfitting with different methods. So remember our pseudo-inverse formula, our famous formula. This is basically the formula for standard linear regression. If we add a bias term, an error term here, this is an identity matrix, P identity matrix, and this is a number that's called ridge parameter, a number greater than 0, then the same pseudo-inverse formula becomes the ridge regression formula. And just small things to remember, this alpha parameter, or sometimes it's called theta parameter, it may vary from library to library, but just remember, for ridge regression or other regularized regression methods, we have an alpha parameter which determines the shrinkage of the model. And this formula we obtained in the previous slide can be written as this formula. And since this is a square, it's called an L2 regularization method. And this alpha parameter is the parameter that we will be using to determine the shrinkage of our model. We will take a look at some examples. You will understand a better way what I mean with this shrinkage. But just to understand, let's say we have 10 independent variables. Okay. If we have a small alpha, then the contribution of weights are greater. but they're more independent and they're not robust. I mean, they change a lot. They're not supposed to change this much. This is not robust. And if you have greater alpha values, you see the effect of the weights shrinks. That's why it's called shrinkage. And it gets close to zero as alpha increases. It's not a good idea to use a very large alpha, and it's not a good idea to use very small alpha. If your alpha is zero, actually this is exactly the same equation as the least square method. And if your alpha is too big, then nothing affects basically, then you get a straight line. So you need to find a balance between zero and this very big alpha. So we have another method called lasso. That's basically the same formula, or more or less the same formula. Forget this part. For ridge regression, we had a square here, alpha times the coefficients matrix square. This is alpha times the coefficient itself. So since this is no square, this is called L1 regularization method. Again, we have this alpha parameter that we will see with the example. And elastic net is basically the combination of these two, actually. That's both L1 and L2 regularization, and that's the formula for the elastic net. Don't worry about the formulas, you will not ever see them again. Just remember, if you would like to create a more robust, more general method with your regularization, it's a good idea to use this regularized method for regression. So before we go into the polynomial regression, let's take a look at our examples for the notebook regularized regression. So that's basically the blah blah stuff. So it's basically a linear model as well, and from linear model you just use ridge instead of saying, for example, linear regression, linear model dot linear regression. Instead of that, we just use ridge regression. And remember to assign an alpha value. We usually assign it 0.5. It's not 0, it's not too big. That's kind of an okayish alpha value for ridge regression. And then it basically fits a line again, but it's supposed to be a more generalizable line. And as you see, we have the coefficients and intercept again for the line. Okay, so let's go into more. So we create a 10 by 10 Hilbert matrix, and we will try to take a look how it behaves with varying alpha. That's basically the graph I have shown you in the slides, actually, this super fancy looking graph. That's just to understand when you have bigger alpha, you have bigger alphas here, the effect of your weights shrinks. That's just to show that here you create 200 alphas, and for this 200 alphas we create a ridge model with different alphas, and then we get the coefficients for the ridge and we plot the coefficients. That was a 10 by 10 Hilbert matrix. Don't worry about what it means. That actually has 10 independent variables, and here you have 10 independent variables, and with increasing alpha, as you see, the fluctuation decreases, and at some point it becomes almost zero. It's never zero, but it gets close and close to zero. Okay, so how we use lasso regression, that's more or less same. From scikit-learn, you import linear model, and instead of getting reach you use lasso. We had used actually 0.5 for alpha. You use different values of alpha for lasso. 0.1 is kind of okay for lasso. Remember, we had a square here for ridge regression. Now we don't have a square here. That means the behavior of alpha is slightly different. And in elastic net, you basically have the same procedure, but you call it a little bit differently. So that's how we actually create our model. And let's see the impact of our of outliers in this kind of regularized method. So let's create a data set. This is the perfect data set. Now we are going to add some randomly generated guys, and then we destroy our data set with this point and this point. Now, when we fit a least square, when we apply linear regression with least square method, we get a prediction like this. Okay, because of this noise. So under normal circumstances, the slope of this fitted line is supposed to be smaller, but because of the outliers, this outlier and this outlier, the slope is higher than we expected. So what happens if we apply ridge regression? See, the ridge regression is supposed to be more robust to noise because it's more generalizable. All these regularized methods, what they claim is actually they are supposed to be more robust to outliers. Okay, so let us try whether that's correct. So that's basically the results we get from ridge regression. If you want to compare, so take a look at this. This is slightly better than our least square method. For example, the distance here and here is more in the least square, and the distance is smaller with the ridge regression. Okay, let's try lasso, whether we get a good result. So that's more or less same with the ridge regression, but it's still better than the normal linear regression because that's a regularized method. It can overcome some noise much better than this square method. And let's see elastic net. Remember, elastic net is kind of a combination of both ridge regression and lasso. That looks slightly better than ridge regression. With the ridge regression, this distance was slightly off, as well as this distance. It's definitely better than lasso with its parameters, and it's slightly better than the ridge regression. Because it's a combination of two regression, it usually behaves better than these two. But depending on your data, it's a good idea to try all these three methods. So moral of the story, if you have noisy data, it's a good idea to use regularized methods, both for multiple regression or linear regression. But as we have seen at the beginning of the lecture, methods like RunZek can take care of noisy data as well. So it's usually a better idea. If you have too much noise, RunZek is much better. If you have okay noise that doesn't really affect your data, then you can use these regularized methods. So that was pretty much for the regularized regression. Okay, so coming back to the polynomial regression, the idea is actually pretty simple. Instead of fitting a line, in the previous part of our lecture, we were always dealing with a line. We will be dealing with a more complicated model that's a polynomial. So that's an nth degree polynomial. It can be a second degree polynomial, third degree polynomial. As the degree of the polynomial increases, the capacity of the polynomial to represent most of the dots increases, which is usually not a good thing, as we have seen in the overfitting stuff. So your model is supposed to be general enough so that it can make good predictions, but your model is supposed to be complicated enough. So this model is not complicated enough to represent this dataset because it looks like a curve. I mean, you can use a line, yes, that's okay, but whatever line you use, that's not enough to represent most of your data, which means a line is not a complicated or complex enough model to represent your data. But a curve is much better in this case. So polynomial regression is still a linear regression, and it uses a slightly more complex mathematics here. Uh, Remember our pseudo-inverse code. So instead of having just x1, now we have x1 square x1 to the power of m. So just this part of the equation changes, okay, with the polynomial regression. You don't need to understand the mathematics behind that, just understand this is a method to fit a polynomial to your data. Not a line, but a polynomial, okay? So let me quickly show you some examples about this polynomial regression. So you can read this stuff just to see the mathematics behind that. I'm importing my libraries. I will be creating this data. Okay, so if you look at the function I have been using to generate this data, that's a polynomial, and that's a third degree polynomial, right? So obviously this is a third degree polynomial, or you can use a second degree polynomial, but if you use a line to express this data, that model is not sufficient. That model cannot represent most of the data here. Okay, so let me import my linear regression model and R2 square. And let's first see what happens when we use linear regression to fit this data. So let's check the R square. That's 0.76. And if you take a look at the line we created with linear regression, that's basically this line. It's not too bad. I mean, that's doing well. But if we had data over here, it was most probably going to be there, right? Because this looks like a curve. If we had data here, then it was going to be here. Now, the more we go to the right in the x-axis, the model was going to behave worse, because this model is not complicated enough to represent this data. So how do we create a polynomial regression? That's quite similar to what we had done. We just import polynomial features, and then we just use this. That's still a linear regression, and you just say it's going to be a polynomial, and basically that's it. And you just say it's a second degree polynomial here, okay? And once we fit a second degree polynomial to this data, what we see here is this guy. And take a look at the R square error. It's 0.91, and the perfect score we could get was 1. That's pretty close to 1. So this is a very good fit. Remember our previous R2 score, that's 0.76, and this is much better than this. And this was a second degree polynomial. So what happens if we fit a more complicated model? Let's say if we fit a third degree, for example, model, then it will be too complicated to represent this data, and it's not a good thing actually. As we discussed before, the more generalizable model you have, it's actually much better. Let's quickly go through this example as well. That's our Boston housing price example. This time we will be using these two columns, this and NOx. And once we plot this and NOx, we get something like this. This looks like a curve as well, right? This looks like a second degree curve. Let's do the same. Let's first use a linear regression model. So this is not good. I mean, this is not representing this data. So we need to use a more complicated model. And you can see that it didn't represent this data by just checking the R2 score. This is not smaller than 0.5, which is still kind of okay, but this is a small number, and you should use a more complicated model. And let's see what happens when we use a second degree polynomial here. I need to be a little bit quick, sorry for that. You can go through all the material after the lecture. Once we create a quadratic polynomial, you see we have a much better R2 score. It was 0.5, it's 0.7 right now. And visually we can see that it's representing it in a better way. So this was a quadratic function. See, it's a quadratic function. It's a degree 2 polynomial. So what happens if we use a cubic function? So we obtain an R score that's better than the previous one. It was 0.7. It's slightly better. It's 0.71. But the shape is fishy, right? I mean, this part of the shape is quite fishy because we don't have too many data here. We cannot judge whether this curve is supposed to hit these 2 points or not. So this is not generalizable from my point of view. Most probably the second solution, the quadratic solution, was much better than the cubic solution. This is not generalizable because we don't have much data here, but we made a judgment with this existing data because we use a complex model. So since we use the complex model, it tried to actually model more data. So moral of the story, polynomial regression is a more complicated linear model than normal linear regression. That's basically fitting polynomials, and if you increase the degree of your polynomial, you can represent more data, which is usually not a good thing. Just try to stick to quadratic or cubic polynomials if you have polynomial data. This is a more complex model than linear models, obviously, but having a more complex model doesn't mean a good thing always. So let's see what I mean with two complex models. So we have seen this overfitting problem. If we have a too complex model, we are likely to overfit, basically. And this was our overfitting example. This very complex, like degree 5 polynomial is actually representing all the training data, but its generalization capacity is very bad, because if you take a point here, the blue model says its prediction should be around 14, but the normal line prediction says it's supposed to be around -9, which is more likely. So overfitting is a bad thing. So we have something called bias variance trade-off. So the variance of an estimator indicates how sensitive it is to varying training sets. Okay, so high variance may result from an algorithm modeling the random noise in the training data, which is overfitting. So if you have high variance, then it is likely that you overfit. And the bias of an estimator is its average error for different training sets. And high bias can cause an algorithm to miss the relevant relations between features and target outputs. That's called underfitting. So we have normal fitting, we have overfitting, and we have underfitting. So in order to understand this bias and variance thing, assume that you have a rifle and you're shooting. Okay. And while you are shooting, what you would like to do is you would like to be as close as possible to hit, right? And you would like most of your bullets to be close to each other. Okay. Shooting inside this circle is bias. And shooting close to each other is variance. Okay. So if you are inside the circle, that means your bias is low. And if your bullets are close to each other, your variance is low. Let's take a look at this. Here, you are not inside the circle, right? That means your bias is high, but your variance is low. Remember from our example, we had huge mean square error, but our residual analysis was kind of okay, which means our model had a low variance. It was always predicting more or less same stuff, but what it was predicting was all wrong. I mean, it has a high bias, it's predicting everything wrong, but it's always predicting similar stuff. So if you take a look at this, we have low bias because most of the things we shoot are inside the circle, right? But the bullets are not close to each other, which means we have high variance. And here we have high variance, which means we have bullets that are not close to each other, and our bullets are not inside the circle. So this is the worst. I mean, high bias, high variance. This is as bad as you can get. So what I mean with overfitting, underfitting, and normal fitting. Assume we have these samples. These blue dots are our samples, and this is the true model function. This is the perfect function we would like to fit. If we use a too simple model like this, a line is a simple model, this is not representing most of my points in a good way. Okay, this is called underfitting because I used a very simple model. If I fit like this is a perfect fitting. This is called normal fitting. My model and my true function are close to each other, right? And if I use a too complicated function as my model, as in this case, so these are my sample points and this is the true function I'm trying to estimate, and this is the function I use. This is something like a 15th degree polynomial. Okay, 15th degree polynomial is representing all the sample data, right? But it's not general enough, so this is called overfitting. So it's not even close to the function I'm looking for. I hope it's clear the difference between overfitting, underfitting, and normal fitting. So at the beginning of this lecture, I said we should split the data set into training set and test set. That's not actually quite correct. In order to avoid overfitting, it's a better idea. So this is a good idea, this is a better idea. It's a better idea to split your data set into three: training set, validation set, and test set. So we use these two guys, the training set and validation sets, in order to calculate the parameters of your model. So you make iterative trials, you use your validation set to measure the performance of your training set, and then you train again and you train again. You come up with something good with your train and validation set. And then you use your test set in order to measure the overall performance of your model. Therefore, you use a test set that you have never seen, and then you can use your train and validation set over and over again to optimize your parameters. So that's another example of underfitting and overfitting. This is underfitting because you have low variance and all your bullets are close to each other, but they're not even close to the truth. This is underfitting. That's low variance, high bias. And this is overfitting. You have high variance and low bias. Okay? Sorry, high bias. So this is yet another example. This is overfitting because you have a very complicated model. This is underfitting. You have a too simple model that's not representing the data. And this is a balanced good fitting. So if our model is too simple and has very few parameters, then it may have high bias and low variance. On the other hand, if our model has large number of parameters, then it is going to have a high variance and low bias. That's called the bias variance trade-off, and we need to find the right or the good balance without overfitting or underfitting. I'm not going to go into the details of that. Okay, the summary of the week. That was a crowded week. That was a difficult week. We started with Ranzek. We saw that it can handle noisy data. And then we have seen 3 performance measures for model evaluation. Then we worked on multiple regression. We worked on regularized regression. We have seen polynomial regression, and we made a discussion about variance bias trade-off.